What exactly are speeds and feeds? Speeds are the tool's revolutions per minute, or RPM. Feeds are the tool's linear or radial movement measured in inches per minute, or IPM. Let's look closer at figuring our RPM. What do we need to know in order to set the RPM? The diameter of the cutter, the material of the cutter, and the workpiece material. What is the average RPM range of a standard milling machine? In high gear, the maximum RPM is around 3,000, and in low gear, about 400. The spindle can rotate as slow as 75 RPMs in low gear, and in high gear, about 400. Let's say that our tool is a half-inch high-speed steel cutter cutting mild steel. This is the most common application in an educational environment. This works well at 78 surface feet per minute. It is worth remembering a shortcut formula for 78 surface feet per minute. To maintain that, a 1-inch cutter would have to run 300 RPMs. That makes 300 a key number to remember because 300 divided by the cutter diameter equals the RPM that results in 78 surface feet per minute. Therefore, 300 divided by a half-inch cutter gives us 600 revolutions per minute. Let's look a bit closer. If a 1-inch cutter rotates 1 revolution, a half-inch cutter would have to rotate 2 full rotations to cover the same distance, or surface feet. So after they had both traveled 78 surface feet in a minute, the half-inch cutter had to rotate 600 times to cover the same distance. Now that we have our speed, the proper method to set the machine to this RPM is to switch to high gear while the spindle is off, and then turn the spindle on. Make sure that the cutter is rotating in the proper direction to make a cut. And then adjust the speed dial to the suggested RPM. We have covered how the RPM represents the tool's rotations measured in minutes. Now let's consider the feed rate, which is how fast a table or workpiece moves into the cutter. This is normally calculated in inches per minute, or IPM. What do we need to know to calculate our feed rate? We need to know the tool's RPM, the tool's number of flutes, and the chip load, which is available on the tool manufacturer's website or charts. You will find that the chip load is proportionate to the diameter of the cutting tool. A 1/1000th chip load is conservative for our half-inch end mill. For our example, we are running at 600 RPMs with a 4-flute, half-inch diameter cutter cutting mild steel. Multiplying the chip load by the number of flutes or cutting edges gives us 4/1000. The chip load is the amount of material removed by one cutting edge. With a 4-flute end mill, every rotation makes 4 cuts. Since each flute cut 1/1000th of material every rotation, the tool must advance 4/1000 into the work each rotation. If the cutter is rotating 600 revolutions every minute and can safely travel 4/1000 every rotation, how far can the tool travel in a minute? Multiplying 600 RPMs by 4/1000 gives us 2.4 IPM. In this illustration, we have mild steel and aluminum being cut by high-speed steel and carbide. Our current application is on the far left. Notice the different cutting speeds. This is not attributed to the increase of chip load, but to the increased RPM. Aluminum is softer than mild steel, therefore easier to machine. Carbide is a harder material, therefore it can maintain a sharp cutting edge at higher temperatures. These materials allow the RPM to increase, so the feed rate will follow because it is based on the RPM. If the feed rate is too slow, the tool will rub, increasing friction and producing heat. This can ruin a cutter and work-harden alloy steels. When a cutting tool is engaged into a piece of material, the friction produces heat, which will eventually break down a cutting edge. To reduce heat, consider using coolant, and by setting your speeds and feeds correctly, you will increase tool life, the safety factor, and the quality of your work.